Yeah, maybe we can start.
Okay, Emma, are you there? Would you like to share your screen? I'm not sure if Emma's... hi, Emma.
Hello, I'm gonna share my slide.
Okay, in the meantime, it's a pleasure to introduce Emma Di Mastrogiovanni, and she'll be talking about gravitational waves from inflation.
And I hope you can see my slides.
Yes.
Sorry, I'm gonna spoil all the surprise.
So you have 35 minutes plus 5 minutes questions, and I'll stop you. Well, I won't stop you. I'll let you know 5 minutes before the end.
That's great. Thank you, Claudia. Okay. Hi, everybody. So I hope you can see my pointer. Yeah. Okay. Very good. So first of all, let me thank the organizers for this opportunity to present my work. And now let me just move the window so I can. Okay. Very good. So yes, today I'd like to discuss gravitational waves from inflation. But before I go into to my slides, let me take a moment to acknowledge my collaborators. So I'm going to give a brief review of gravitational wave from inflation, of course, from the biased perspective of the work that I've done with these very nice people here. And so let me show the main novel look at the summary. So we know that inflation predicts a stochastic gravitational wave background. So the questions I will be asking is that I'm interested in: how does this background looks like? What kind of information can we extract on inflation from the gravitational wave background? And what are the instruments and the observables that we have to characterize it? And in particular, these are the main quantities that I will be focusing on, and I will be going through each one of those, and both a little bit from a general perspective and also by referring to some very representative classes of models. So let me just say a few words about inflation. I will be focusing on how we can test the very real universe with gravitational waves. So I'm looking into the early era of exponential expansion that we likely had during, at very early times in the history of a universe. And we all know why inflation is needed. One thing that it nicely does is to explain the nearly perfect uniformity of the cosmic microwave background across distances that whose nearly perfect uniformity could not be explained with sub-horizon plasma physics. And inflation also explains the origin of the tiny fluctuations that we observe in the cosmic microwave background, among other things. And throughout this talk, I will be referring to SFSR as single field slow roll. So I will be mentioning this as, I will be using these 4 letters to indicate the simplest inflationary scenario, where you have inflation driven by a scalar field in slow roll. And in the inflationary picture, as I was mentioning, the inflaton field fluctuations are believed to be the origin of the cosmological perturbations, and at the origin, therefore, of the temperature anisotropies in the CMB, or the largest of the structure in the universe. So let me move on to gravitational waves, which is what I will be focusing on. So in my notation, I will indicate them as gamma. So when we think about gravitational waves, we're thinking about the traceless and transverse component of the metric, which I'm going to indicate with gamma ij, and So if we apply these two conditions, we end up with 2 degrees of freedom, which are the 2 polarization states of the graviton, the plus and the cross. And during inflation, if we want to know what happens to these metric perturbations, tensor perturbations of the metric, we can write down the equation of motion, and it's going to look like this. So on the left-hand side, we have the usual wave equation with the addition of a term which contains information about the expansion of the universe, because it includes h. And then on the right-hand side goes everything else, everything that comes from the energy momentum tensor that may contribute to such an equation. So in this talk, so let's say during inflation, we can have, let's say, if we look at this equation, it's a second order equation, and it's expected to have the most general solution to be built by 2 contributions. One is the solution to the homogeneous equation, which one gets by setting the right-hand side to 0 and deriving the most general solution, plus the solution to the inhomogeneous equation. So the former, the solution to the homogeneous equation, is what we refer to as gravitational waves from vacuum fluctuations. And it turns out that during inflation, you can actually generate gravitational waves this way. Now, the right-hand side is never exactly 0 during inflation. There's always some contribution to the right-hand side of this equation. So there is an inhomogeneous solution, or solution to the inhomogeneous equation. The thing is that if you have just one field, the inflaton, then under, let's say, the simplest assumption that you can make, this contribution from the inflaton to the solution to the inhomogeneous equation can be neglected. So that's why people always, when they think about gravitational waves from inflation, they think about the vacuum fluctuation, so the production of gravitons out of the vacuum. But as I will be discussing at some point during this talk, if we go beyond the simplest scenario of a single scalar field in slow roll, we may run into fields that can contribute in an important way to the right-hand side of this equation, and so the inhomogeneous solution needs to be accounted for. So this is I'm just anticipating some of the things that we'll be discussing later. But for now, let me just stay focused on the vacuum fluctuations, just to keep it simple and to the basic scenario. And we have to remind ourselves that inflation predicts this background of gravitational waves across a very, very large range of frequencies, from the very, very low frequencies, which can be tested with the cosmic microwave background anisotropies, all the way to the very high frequencies that can be probed with terrestrial interferometers and beyond. So if we take that vacuum fluctuations and we plot the result for the energy density of gravitational waves per logarithmic units of the frequency or wave number, we get for a tensor to scalar ratio, so an amplitude of the gravitational waves as large as it is allowed by CMB bounds, by current CMB bounds, we get something that looks like the black line in this plot. And as you can see here, I'm showing the sensitivity curves of many of current and future detectors, including here what we can do with PTA, and here with terrestrial space interferometers. As you can see, most of them would be unable to probe gravitational waves from inflation. So on small scales, something that is vacuum fluctuation will go most likely undetected. On the other hand, of course, there is room on the very large scales, so very small frequencies, to access this signal with CMB. For example, here I'm plotting what the sensitivity limit of an experiment like LIBIRD would be looking like. So now this behavior of the gravitational waves from vacuum fluctuation in the simplest scenario is what we refer to as a red tilt. So this line is nearly perfectly straight. Actually, it goes down just a tiny bit when going from the very large to the very small scales. And this is not the only feature of the vacuum fluctuations, of gravitational waves from vacuum fluctuations. Another important, this is the red tilt that I just mentioned. Another important prediction is that the left and the right helicities of the gravitational waves behave exactly the same. So, for example, they have the same amplitude for the power spectrum, and then also within this scenario, with this simplest scenario, we can predict a one-to-one correspondence between the energy scale of inflation and the amplitude of the gravitational waves, which is what this relation over here indicates, or the one over here. And then the last prediction that characterizes this scenario is typically a very small non-Gaussianity, which I will get to in a little bit. So these are the predictions. Now, of course, if we want for interferometers to be relevant for inflation, we would need a blue tilt, something like a blue tilt, or some kind of bump that somehow overlaps with the scales at which interferometers operate, or PTA. And as I will discuss, I will try to argue during this talk by showing one class of models. These are possibilities if once one goes beyond the simplest scenario. So for the next few slides, I will be addressing what we can say about sources during inflation of gravitational waves due to the presence of fields beyond the inflaton, and how with these sources we can easily violate the fundamental characteristics of the gravitational waves from vacuum fluctuations. So there is a lot of work in the literature on sources. As I'm listening here, people have been considering scalar fields, vector fields, fermions, additional tensors, for example. And I'm just going to pick one class of models, which is representative of for this kind of mechanism of gravitation, representative in terms of gravitational wave production, and that has been, let's say, very popular and very popular for inflation for a number of reasons. So the class of models that I'm referring to is characterized by the presence of axions and by the presence of gauge fields. So as soon as you consider, so axions were historically introduced for in order to solve the so-called eta problem. And then again, if one starts taking into account gauge fields, which one would say, okay, I don't see why not, because we know a few gauge fields, and then you are basically forced to write down this kind of coupling between the axion and the gauge fields. And then, so from this coupling, a very interesting phenomenology can arise, and people have been looking at these models for a number of reasons. In the context of reheating, baryogenesis, primordial black hole formation. The reason why I will be discussing it in this talk is for production of gravitational waves, and in particular chiral gravitational waves, and in particular gravitational waves that do not necessarily have the red tilted spectrum that we saw in the previous slides. So this is my motivation for this talk. And in this slide, I've written a very incomplete list of references, of interesting papers that have been written on this topic. So let me just take one example, because there are many models with axions and gauge fields, and they all have some features. There are some features in common, and so in this particular model that we proposed with Matteo Fasiello and Tomohiro Fujita a few years ago, we extended the so-called chrononatural inflation model, which had was formulated, was very interesting, but it could not be bring to agreement with observation, so we extended it. And in this particular model, what we have is an inflaton sector about which we are agnostic, and then we have a spectator sector which is contains this gauge field and this axion. The axion is chi in this case, and is not the inflaton. And this is the crucial feature of this model, because the axion being separated from the inflaton gives us a lot of freedom in terms of phenomenological predictions. So in this case, so what happens is that you have your axion that is rolling down its own potential and is coupled to the gauge fields, and this coupling results into dumping of energy between the axion, from the axion to the gauge field. So you have gauge field production. But then, because we are, in this particular case, we are dealing with SU2 gauge fields, the gauge field perturbations have a TTA component, which then couples linearly with the metric, the translated transverse component of the metric, so with gamma. And so what you have in this model is a linear production of gravitational waves from the gauge fields. And the other interesting thing, and by the way, this coupling here, which is linear between the gauge field perturbations and the tensor modes of the metric, is not possible to have the same coupling, of course, between gauge fields and the inflaton, because the inflaton is a spin zero, and therefore this explains why you have more freedom in this model to, let's say, influence the tensor sector without too much affecting the scalar sector, though you affect it in some way, but not as much as you would with other types of field content. So in this case, the other nice thing that happens is that you have parity violation in this model, and what that brings is a different type of amplification of the gauge fields between the two helicities. And then, because each helicity of the gauge field is sourcing the corresponding helicity of the gravitational waves, one of the two helicities of gravitational waves is overproduced compared to the other, and therefore you end up with what we call a chiral signal, which means that you have an imbalance between the left and the right of gamma. So you have a chiral gravitational waves. And the other important thing to remember is that because the sourcing of the gravitational waves is related to the dynamics of the axion, and the axion is pretty much free to have a dynamics of its own. It doesn't need to follow the inflationary evolution, the evolution that would be the evolution of the inflaton field. Then it can have, for example, this can result into a spectrum for the gravitational waves that may have a bump, or it may be blue tilted or red tilted, depending on the range of scales you're looking at. So depending on your parameter space in these models, you have the freedom to have a different types of frequency profile. And then, so this is, let's say, one possibility, say the most general possibility, the most likely prediction in our particular model is something like this. And so it's like it's a bump, and this bump can occur at different scales depending on your parameters. And there's a nice paper by the group Eiichiro Komatsu's group, Eiichiro Komatsu and collaborators, where they did some forecasts to see if within these models you can observe this bump, for example, with LIBERT or with LISA or SK or AT. And the other, as I mentioned, we have chirality, so the left and the right amplitudes are different for the gravitational waves, and this is again in contradistinction from with respect to what happens during in basic single field slow roll inflation, where you have a non-chiral signal. We have a number of ways to test chirality. On CMB scales, we would be looking for non-zero TB and EB cross correlations. Those objects are normally zero, are zero if you have parity conservation as far as the primordial signal goes. And again, Chiros and collaborators did some forecasts for our model to see how much R would need to be for a detection of these cross correlations with LiveBird. And now it would be also interesting to detect chirality on small scales, because in principle, these models give chiral signal, which can be also on small scales. And there is a very, this is not my work, but I like to point out because it's a very interesting set of papers that people wrote to see how we can test chirality with interferometers, for example. And the basic fact is that if you have a planar detector, the geometry prevents you from distinguishing a left from a right circularly polarized gravitational wave if you are in the presence of an isotropic stochastic gravitational wave background. So what you need to do is to, you basically, in order to overcome this, you want to use different detectors at once, which are non-coplanar. And you can do, and there is work that has been done for ground-based, for space-based in this respect. And the other thing that you can do, which then relies on oh, I think there are questions somewhere about tectonic instability. Which form of the potential are you using? Yeah, there is no instability in these models. And the potential for the axion could be like a cosine. So this U of chi is typically a cosine. It's typical potential that one uses for axions. But I have to say that the general mechanism does not depend, I mean, the general features that do not depend on the specific potential that is chosen. So let's see. Okay, thank you. So I was going to say, so you can measure the chirality by using different non-coplanar detectors, or you can use the fact that the detectors are moving. This is true both for the detectors on Earth and the detector in space, because they're all moving with the solar system. And so what you basically, if the detector is moving, the stochastic gravitational wave background, even though it's isotropic, and this is like the assumption that we make a priori, because we expect it to be at least to leading order isotropic. So this is from the point of view of the detector that is moving, there is no longer a perfect isotropy, and so one can use the dipole that is kinematically induced by the peculiar motion of the detector in order to extract information on the anisotropy. So this is another possibility. And then you can, I also refer you to this paper for the similar analysis performed for PTA. So again, Chiro did some forecast for, I refer you to that paper for forecast for our model for what a LISA-like or BBO-like detector would be able to do in terms of chirality. When I say LISA-like, of course, I mean something that is an extension of LISA that considers two constellations, because again, at the level of the monopole, you cannot do with one constellation only. So to summarize, this is just one class of model, of course. We don't know if that is the correct description of inflation, but because it's interesting, this class of models is interesting for a number of reasons. I thought it would be a good example to point out why the let's say 3 so far of the basic prediction that are associated with gravitational waves from inflation when people think about vacuum fluctuations are not can be easily violated in these models. Of course, these models also produce vacuum fluctuations. It's just an additional source that you have and can overcome the vacuum fluctuations. And so let me go to the last point, to the non-Gaussianity. As I mentioned, in the prediction is for the vacuum for gravitational waves from vacuum fluctuations that they are nearly Gaussian. So what does that mean? When we talk about non-Gaussianity, we think about going beyond the 2-point function. So the next after the 2-point function, we have the 3-point function or the bispectrum. So we're looking at 3-point correlations. And what these objects, the way we characterize non-Gaussianity is by an amplitude and by defining the amplitude and the shape function. So the amplitude is just the bispectrum 3-point function in Fourier space divided by the Power spectrum square to make it dimensionless. And the shape means the momentum dependence of this bispectrum. So different shapes are predicted in different models, and that's why it's important to look at both amplitude and shape. And what non-Gaussianity does in practice is to probe the interactions of gravitons. So if you have if you consider just GR, then you're going to have the self interactions. If you start considering additional fields, then these fields will interact with the gravitons and will somehow contribute to these 3-point functions. So what happens in basic single field inflation is that the amplitude of these diagrams is very, very small. On the other hand, if you start looking into models like the one that I discussed, besides these objects, you also have interactions mediated by the gauge fields, which can enhance your signal for non-Gaussianity. And these two diagrams are examples of what can go on in these models, where you have this gauge field which interact linear with the gravitons, and they can change the value of F and L of the amplitude. And again, in this, I refer you to this paper for a forecast for where they show that this kind of signal would be detectable by a coming CMB mission like LightBurn, for example. And then the same thing you can have in these models for interactions between the gravitons and the scalar perturbations, the curvature perturbations. Again, these can be mediated by the gauge fields, and so you can end up with a larger amplitude. And this is some of the literature where you can find these calculations, and there is a lot more that came after that. Okay, so this is, I guess, the point that I wanted to make with these models. Now, let me just go back to this non-Gaussianity. So as I said, we characterize it with an amplitude and a shape. In these models, what you have is a shape that is very highly overlaps with the equilateral shape. It means that the majority of the signal, the bispectrum signal, is coming from the configurations where the 3 momenta that I'm correlating are very similar to one another. So this is what we call equilateral shape, as opposed to something like a squeezed. So in these models, for a number of reasons, we only have equilateral type of non-Gaussianity. But now, just to make it complete, and let me focus on the squeezed. And of course, the squeezed non-Gaussianity has nothing to do with these models. You're going to look into a completely different class of models. And the squeezed non-Gaussianity also gives me the opportunity to discuss tests of non-Gaussianity at small scales with interferometers. So we all know how to constrain, all of us have been working on this, but we all know that non-Gaussianity has been constrained with cosmic microwave background anisotropy, and people will continue to work in that direction with a new experiment and to put more constraints. But on the other end of the frequency spectrum, on very small scales, let's say interferometer scales, we also like to constrain non-Gaussianity for these models that generate a large signal at interferometer scales. And now, what does that mean? So if you're looking at the bispectrum, you want to compute a 3-point function. So you can think of the length of the side of the triangle as proportional to the gravitational wave frequency that you're considering. And then, of course, the direction of the incoming gravitons will be the direction of the momenta. Now, for gravitational, let's say at small scales, what goes on is that you have basically a decorrelation. So you cannot directly measure the biospectrum. And this occurs, so you cannot measure that object on small scale that we discussed earlier. And this occurs because as gravitational waves propagate in the perturbed universe, the mode function of the graviton acquires a phase shift, which is due to Shapiro time, which is basically due to Shapiro time delay. And this phase shift is direction dependent. So signals coming from different direction acquire different phase shift. And when you go and compute a bispectrum, so Claudia, is the 5 minutes those for the questions or those for the talk? Sorry.
For the talk. After that, I still have 5 minutes for questions.
That's great, thank you. So this Shapiro time delay basically causes a decorrelation. So even if you have a three-point function signal at the origin, then after propagation, this signal basically disappears. And so you would, okay, so if we say it in this way, we would naively then conclude that you cannot directly measure the bispectrum at interferometer scale. So even if you have a bispectrum in your model predicted by your model and a large signal interferometer scale, then you would not be able to use that. But there are exceptions to this. And one of these exceptions is ultra squeeze non-Gaussianity. So if you have a signal, if your model predicts a large bispectrum in the squeeze configuration, so it predicts a correlation between one very long wavelength mode and two very short wavelength modes. Then what happens is that this will induce some anisotropies at the level of the power spectrum for gravitational waves. And this is like looking at two signals originating from the same patch, if we want to like have a picture of this process. And so one way to constrain the bispectrum is to look for anisotropies in the stochastic gravitational wave background. So when I talk about anisotropies, what I'm doing is I'm writing down the energy density, the spectral energy density for the stochastic gravitational wave background, and I'm separating it, a constant. Let's say a direction independent part from a delta GW, which will depend on the direction. So now let me say more precisely how these anisotropies come about from the ultra squeeze non-Gaussianity, and then towards the end I will also mention other types of anisotropies that we can expect to find in the stochastic gravitational wave background, and how to possibly distinguish those from the ones that I'm describing here. So as I mentioned, if you have a squeeze signal, then you are going to induce, let's say, a shift or an isotropy in the two-point function, which is proportional to the long wavelength mode and to the amplitude of the bispectrum of the non-Gaussianity. And this idea dates back to work by Mark and collaborators, and Mark and and other people, including myself, which was dubbed as fossils. So if you have, for example, a tensor bispectrum, this will, in the squeeze limit, that this will induce an anisotropy in the power spectrum of the tensor perturbations. Similarly, if you have a scalar tensor bispectrum, can induce an anisotropy in the tensor perturbations, and this will give us information on the curvature perturbation, which is long wavelength, and on the amplitude of this three-point function. So I'm almost out of time, so I'm not going to spend too much time on the models, but this slide basically summarizes typical classes of models in which these signatures can be important. And as you can see, single Fislorov is not one of those, because it is typically characterized by a very, very small signal, unobservable in the squeeze limit. So the squeeze limit is very important to test the presence, for example, of additional fields, no excited initial states, broken space diffs, and similar things. And just so let me say just a couple of words to conclude. Besides the anisotropies that are induced from non-Gaussianity that are predicted by these models, we also expect other types of anisotropies. One class of these anisotropies, those due to propagation through the perturbed universe. So just like you have in the CMB Sachs-Wolf, integrated Sachs-Wolf and Doppler effects, you will find the same type of effects in the gravitational wave background from propagation through structure. And if you go to the very large scales, the Sachs-Wolf effect will be the most prominent. And in this case, also you expect the density, the gravitational wave perturbations, the anisotropies in the stochastic background to be proportional to the long wavelength perturbation. So one way to distinguish those, for instance, from okay, we know what the amplitude of those is, and what one can do is then these objects are these anisotropies are naturally correlated with the CMB anisotropies, and these correlations can be used to bring further information on the nature of these anisotropies. And this is a very recent work that we did with our student Amit Malhotra at UNSW. So these cross correlations could also be useful to, in the case where you have a very noisy map for gravitational waves and anisotropies and you want to try and extract the primordial signal. So if you have a sufficiently large non-Gaussianity, then you in principle could measure these cross correlations. So let me just leave my final slide here, and I'm happy to take any questions.
Thank you very much, Emma. That was an excellent talk.
Thanks everybody for the attention.
Is there any, I know we had some questions already. Is there any question right now? Feel free to raise your hand. Otherwise, or write it on the chat. We'll be monitoring that. I can't see anything right now. Maybe people are formulating their questions. I had a quick question though in the meantime, before someone else asks. In your model with gauge and the axion, is there possibly any other smoking gun signature beyond the ones you mentioned, beyond like chirality and other things like that? Just for instance, from the vector fluctuations, production or anything else that could come hand in hand with the peak you mentioned.
Yes, in fact, there are a number of, let's say, so there are a number of, as I listed in my first slide, there are a number of reasons why these models were proposed. And so you can have primordial black hole formation in these models. And so that would be another smoking gun for these models. Of course, you need, I mean, not the whole parameter space can give you enough, can enhance the curvature perturbation enough so that you have primordial black holes. And then besides the, this is one example. And then besides the primordial black hole formation, then you can also have, of course, production of gravitational waves of second order, depending on your specific realization that you are considering for axion gauge field models. And you could also have, then you can think of gravitational waves arising from the merger of these black holes that are generated. So you could have different types of signatures. Yeah. In the specific model that we consider, people look at primordial black hole formation as well. So yeah, that would be another.
I guess those come at different frequencies. So the gravitation.
That's right. Yeah, that's right.
But for what about the production of vector fluctuations?
Yes, you can. So if you have, for example, that I guess those are more prominent if you have a U1 gauge field instead of an SU2 gauge field. And in that case, actually, the vector fluctuations are the main protagonist. Let's say the fields that generate your gravitational waves more than any other field. So those will be for the U1 scenario, especially.
Okay.
So you can have the same type of generation, except that instead of having a linear generation, you have like a three-leg diagram for the two vectors generating one tensor.
That makes sense.
But then the features can be very similar, and you can also have some spectrum that grows on the small scales.
Okay, very interesting. Thank you. We have time for one very quick question. If not, let's thank Emma again.
Thank you.
Thank you very much for this excellent talk. And then we can go to the next speaker. So Zongzi,
Hey. Hello.
Hi.
Yes. Can you hear me?
We can hear you fine. Yeah, we can't see your
Okay,
screen
good.
right now.
Sure. Let me share my screen.
And just to let you know, I can monitor the questions while you give your talk, so don't worry about looking at the chat.
Okay.
You
Thanks.
have 25 minutes, 20 minutes
Okay.
for questions. I'll give you a hand at 15 minutes.
Okay, cool.
Okay.
Yes. So can we start?
Yeah, you can start. It's a pleasure to introduce Zongzi Zhenghu, who will be talking about recent progress in cosmological collider physics.
Okay, so hello everyone. Many thanks for the introduction, and many thanks to the organizer for giving me this chance to present this topic. I should say this is not immediately related to the main topic of this conference, which is gravitational waves. But toward the end of this talk, I may mention some link to the gravitational wave physics. So the topic is the cosmological collider physics. Of course, this is a fancy name of non-Gaussianity, which has been discussed a lot by Emma's very nice talk. And in my talk, I will mention some recent work we did with our collaborators listed here. So let me begin by explaining what is a cosmological collider. So the idea is actually very simple. We are drawing analogy with a real ground-based collider. So here I'm drawing a funny picture. Left side is the cross-section of ATLAS detector at Large Hadron Collider, and the right side is actually a chronological view of our universe, its whole history, but I deliberately redraw it into a circular shape. And you can see there are layered structure just in parallel with a real detector. I want to make this analogy because the layered structure of our universe evolution actually provides us a wealth of data that we can use to probe what was actually happening at a very early stage of universe at its center. So it is believed that a cosmic inflation has happened before the thermal Big Bang, actually. And this inflation can take very high energy. If you measure this energy in terms of Hubble parameter, this can be as high as 10 to the 14th GeV. So it's right here. And if you compare it with the energy of current most powerful collider built by our human beings, is Large Hadron Collider is here, you immediately understand why we are talking about cosmological collider here today, because the inflation provides us a huge energy that is much beyond the reach of any ground-based collider in the foreseeable future. So this is a good chance for us to try to probe ultra-high energy physics. But what is actually the physical work of a cosmological collider? So the physics behind a cosmological collider is this. So here I am talking about a scalar non-Gaussianity. Emma has already given a very nice introduction to the non-Gaussianity. But here I am looking at a particular channel that produces this non-Gaussianity. That is, we have the spontaneous particle production during inflation purely from quantum fluctuations. This is very much like the Schwinger pair production already mentioned in Jerome's talk in this session, in last session. So this Schwinger pair production works not only for the scalar perturbation itself, but also for any fields that exist during inflation with mass up to Hubble scale. So any fields with a mass up to Hubble scale can be spontaneously produced with unsuppressed rate. And once produced, these particles are quickly redshifted and diluted. By redshifted, I mean that their momentum are quickly diluted to essentially zero, leaving a non-relativistic state. So these particles will be oscillating like a clock with a constant physical frequency, which is simply its mass. Now, if this particle with constant mass couples to the scalar perturbation that solves the density perturbation we see today, then this particle can leave a distinct signature on the three-point correlation, especially in this squeezed limit, which also mentioned in Emma's talk. So why the squeezed limit? We know that these scalar perturbation modes exit the horizon according to their wave number. So large mode leave the horizon earlier, small mode leave horizon later. So by choosing a squeezed configuration, you are actually setting up a hierarchy in time so that if you measure the three-point function as a function of squeezedness, as the momentum ratio, you are actually measuring the time evolution of the intermediate massive particle. So if I put all this word into formula, if I calculate this three-point function mediated by a massive particle in the squeezed limit, what I will get is a shape function like this. Now, since I'm working in the squeezed limit, this shape function will depend essentially only on the long mode K3 and short mode K1. And the result of this shape function had three pieces. So first is the amplitude A, which depends, of course, on the coupling to the coupling here, lambda, and also the mass of the intermediate particle. But very important is the dependence on this momentum ratio, the momentum ratio K3 over K1. You can see that there's an exponent here, nu, and this exponent nu is in 1-to-1 correspondence with the mass of the intermediate particle m in the unit of Hubble. In particular, if the mass of the particle is greater than the 3/2 of Hubble, you realize that this nu parameter is actually an imaginary number. And once you have an imaginary number in the exponent, you immediately realize that this shape function will be oscillatory in the momentum ratio. So if you are able to probe a bispectrum generated by this process, you will see oscillations of this bispectrum as a function of momentum ratio. And by measuring this frequency of oscillation, you are directly measuring the mass of the particle in the unit of Hubble. Remember that the Hubble scale during inflation can be as high as 10⁻⁴ GeV. So this channel provides us a chance to produce and measure a very heavy particle with mass up to 10⁻⁴ GeV. And lastly, but not least importantly, is the angular dependence here. So if there's a spin S particle mediating the bispectrum, you will see this Legendre polynomial dependence on the angle theta. The angle theta is the angle between K1 and K3, which is a direct consequence of angular momentum conservation. So in this right plot, you see two complete cycles. If you go around the circle, suggesting that you are seeing a spin 2 massive particle, which is a massive graviton. So this is a basic picture of a so-called cosmological collider. But after introducing this, there are immediately several caveats I need to mention. So that is how not to use the cosmological collider. I mention this because the inflation is a very complicated physical process. And the mass of fields during inflation is not necessarily the mass, not necessarily its bare mass. It's not necessarily its mass in vacuum. So for example, there are thermal fluctuations coming from the Hawking radiation. We know there's a horizon during inflation, so there are Hawking temperature. And this temperature can contribute a thermal mass to the particles. And also there are inflaton background. If you couple the inflaton to this field, this inflaton can typically introduce some masses to this particle, so that all this complicated physics can strongly affect the spectrum of particles. Is someone asking a question? No. Let me continue. So for example, here I'm showing you the spectrum of standard model particles. And the general lesson is that typically their masses are lifted to Hubble scale. This is both a blessing and a curse for cosmological collider physics. It is good because you will have states with mass around Hubble, making sure that you have a chance to measure some non-trivial oscillations. But the bad thing is that the frequency that you read from this oscillation is not necessarily the true mass of this particle. So you detect the oscillation with a mass up to 10 to the 14th GeV. This does not necessarily tell you this is a new particle with that heavy mass. It's probably just a addressed mass of standard model particles. So it is very important to make sure that the mass you are detecting is a real mass, but this is actually challenging. Another thing, another caveat is that actually that typical signal from this channel are very tiny and negligibly small. So there's no hope to see them. And now, unless you tune your model, if you tune your model, you can always have a large signal, but this is not considered generic. And speaking of the size, we typically define a dimensionless parameter called FNL that measures the overall amplitude of this shape function. And the one particular reason I am talking about this today is that although we have not detected non-Gaussianity yet, in the future, actually very near future, we will have new probes of large-scale structures that just aim at probing non-Gaussianity and pushing the precision down to 0.1, order 1 or order 0.1 in the next few years. And if you want to be very futuristic, there's actually a chance to do 21 centimeter tomography, and people predict that you can actually measure very small non-Gaussianity down to 0.01 by using this. So by opening up this several order of magnitude parameter space, you can ask yourself what new physics you can learn. Then the task is, can you find any good physical models that provide you cosmological collider signals with an amplitude in this range? And as I said, this is in general actually very challenging. The reason is the following. So to compute the size of this non-Gaussianity, you apply the standard in formalism calculation. But instead of doing this complicated calculation, you can also apply a very simple estimate. You just multiply all the vertices and the propagators in your diagram and multiply by some normalization factor, you immediately get your FNL. The problem here is that typically, if you want your signal to be large, you want your vertices to be large, you want your couplings to be large. But a large coupling in general introduces a large mass correction to the intermediate particle. And once you have a large mass, you immediately suffer from the Boltzmann suppression. So this is the case for most of simple effective field theory couplings. You can write down consistent with the symmetry. For example, if we demand the shaped symmetry of inflaton, and if we write down this dimension 6 coupling of inflaton phi to a massive particle sigma, then we immediately realize that the rolling of inflaton phi dot will in general introduce a huge mass correction to sigma, unless you have a huge cutoff scale. But again, a huge cutoff will render the signal too small to be seen. So this is a general problem of realizing the large signals in cosmological collider. So we can actually try to scan all the possible EFT couplings to see if there's any loophole to this argument. And it turns out that there's a unique loophole if you choose to respect all the existing symmetry of space-time and the inflation. sector, then this loophole is the dimension 5 coupling of the partial mu phi, the derivative of inflaton to a current. So this current is in general a CP out current, which can be either a fermion chiral current, or for gauge boson, it can be a Chern-Simons current. You can even couple this phi to the RR dual, which produce helical gravitational waves, which is, of course, well known. So the merit of this dimension 5 coupling is that it acts actually as a chemical potential for the particle production. So that the particle production process here is not controlled by the Hubble expansion, but by the rolling of inflaton. And then we know that the rolling of inflaton is much quicker than the Hubble expansion, so that this gives you a huge production rate. And you can make use of this huge production to enhance your signal greatly. So here I'm just showing you the mode function of a vector boson in the presence. In the presence of a chemical potential, and you can see huge enhancement relative to no chemical potential. And there are some interesting physics you can do. I will just mention very quickly. First, you can try to produce heavy right-hand neutrinos, since the seesaw scale is very close to the natural inflation scale. And in this case, you can produce order 1 non-Gaussianity, even it's from one loop. And also you can do gauge bosons. The interesting thing for gauge boson is that you can try to test CP violations here, very much like you do for ground-based collider. You look for 4 final state process. Here you look for trispectrum, and you look for angular dependence. Any odd angular dependence tells you you have a CP violation. And in the last few minutes, I mentioned some non-minimal scenario. So the scalar perturbation we see today is not necessarily from inflaton. It can also be from something else. For example, it can from stem model Higgs. We actually cook up a model which we call cosmological Higgs collider, meaning that if you can modulate the reheating process by a stem model Higgs field, then what you are actually measuring in the cosmological collider signal is the Higgs interaction. So you are detecting Higgs interaction at a very high scale. And we have a successful model. It's not very cute, but it's successful in generating large signals. And the interesting thing here is that all the couplings and masses are known, so there's no free parameters in this model. You can even imagine to calibrate the cosmological Higgs collider from these signals. And last, I also want to mention that there's a chance to measure the so-called missing energy in the cosmological collider. This is actually another name of cosmic fossils. People know this very well. But in general, in original cosmic fossil proposal, people are actually measuring a 4-point correlation. And we are asking if you can measure this light field in the 3-point function. The answer is yes. If this light field also giving mass to a heavy particle, and you look for the decaying of the oscillation feature of this heavy particle, you will see the loss of coherence due to the quantum fluctuation of the light field. So in typical case, the constant mass will give you alpha equal to 0 in this oscillation shape. On the contrary, if you have a missing energy that can a deviation from 0. And this will be a signature of cosmic fossil or missing energy in the case of 3-point function. So this is a status summary. We have quite a few models predicting large non-Gaussianities in the range that can be probed in the near future. And I think I have only 1 minute. Let me mention that there are also theory challenges because computing these diagrams, these processes are very difficult theoretically, and there are some recent development in formal techniques in computing this. And we are also trying more pragmatic approaches to directly attack the signals by numerical computation. And last, let me say just one word in relation with gravitational waves. So all I have been said are for scalar perturbation, but all the things also apply to the gravity. If you consider tensor mode, then there will be new kinematics. For example, the angular dependence can be more interesting because now two-component intermediate particle. So you will have, in connection with observation, you can also ask whether you can try to measure this non-Gaussianity with joint data from CMB and also space-borne gravitational telescopes like LISA. These are no longer some crazy ideas. Now people are carefully considering these options. And I hope in the next few years we will have more work in these directions. So I will stop here. Thank you very much.
Okay, thank you very much. Very interesting talk. And we have a few questions in the chat. There's one from Yen Huki. I don't know if you want to ask it yourself. Otherwise, he's asking if you can explain the gravity flow at FNL of 10 to the minus 2 on slide 5.
Yeah, okay. Let me try if I can go back. So by gravity,
reformulate if you want.
Yeah. So this is a cute part of non-Gaussianity. This is not like the tensor mode, right? The tensor mode, the size of tensor mode is very much depend on the scale of inflation. Of course, there are exceptions, but for non-Gaussianity, there is a guaranteed signal that is a self interaction of a scalar mode, which is just from gravity. We know gravity is there; it will produce an FNL of size 10 to minus 2. So if you have a machine that is capable of measuring FNL down to 10 to minus 2, then this signal is almost guaranteed.
Okay, thank you. And Anish, you had a question?
The question is about whether we can see this from 21 centimeter. Yes. I'm not expert on this, but according to the paper I list here, there's some study on if you marginalize all the unknown nonlinearity of gravity of foreground, then how much precision you can achieve by using 21 centimeter tomography. So if you just disregard all this foreground contamination, in principle, you can go to 10 to minus 4, which is of course crazy. But even if you marginalize over all those unknown, you can still achieve 10 to minus 2 according to this study. But I admit it's very challenging to see the dark edges signal of 21 centimeters. So it will be very challenging. So I said it's very futuristic.
Okay, thank you. Enrico posted a comment. Would you like to comment in real life, Enrico?
Sure, I can say just because the question of what is the gravitational floor, what is the lowest you can go? And I think that's an important question. If it is 10 orders of magnitude, maybe our civilization will never measure it. If it is 2 orders of magnitude away, maybe we will. And I think that's really important, maybe not in the next 10 or 20 years, but in the next century. So I think that we establish what it is, and I think it is correct, it's of order of 10 to the minus 2. And this is expected because gravity is a nonlinear theory, so you cannot avoid those nonlinearities. There was quite some confusion as to what precisely the signal is, because in Maldasena's calculation, you might think that the signal should be some equilateral contribution of order ns minus, squeeze contribution of order ns minus 1. That's not correct because that's not visible in physical measurements. But once you remove the gauge artifact and you go to the physically local observable, the result is of a similar order of ns minus 1, but it has an equilateral shape. And a detailed study was given in this reference by us. So I thought if people want to see the calculation, that's where it was performed.
Yeah. Thanks for this excellent comment. I completely agree. So that's actually a very cute computation that the consistent relation of non-Gaussian is actually non-observable at leading order. Exactly because the mode that is modulating the short mode is also modulating us. We are free fall in that long mode. That's why we cannot see this non-Gaussianity. But just as Enrico pointed out, you can look for an equilateral region of non-Gaussianity, and the prediction is 10 to minus 2.
Can I ask a follow-up question?
Yes, go ahead.
Yes.
Yeah, so does this mean if the new physics signal is below 10 to the minus 2, then we cannot observe it? Or maybe even if you have the gravity floor, but look at the finer pattern, you can still dig out the signal?
Great. I imagine that you have neutrino flow in mind compared to dark matter direct detection, but this is actually not the case. Actually, most of non-Gaussianity will be larger than the cosmological collider signals, but those are smooth background. By cosmological collider signal, I mean these oscillatory features. So the strategy is that you first try to detect non-zero non-Gaussianity, and then try to look for those small ripples on top of that. And since these oscillations are actually some non-local correlations, they can be identified unambiguously out of the background. So that's the idea.
Thank you.
Okay, thank you. I think it's a good time to wrap up.
Okay.
Yes, again, and then we can move to the next talk. So if you want to share.
Did I unshare my screen? Oh, sorry. I'm sorry. Give me 1 second. Okay.
Okay, and I think Mark, you should be able to share now. So while Mark is sharing, in the meantime, I'll introduce him. It's a pleasure to have Mark Mikulski, who will be talking about black hole, gravitational waves, and avenues to new physics. I can see your screen, just not in presenter mode.
Okay, give me 1 second here. I will fix that. Sorry.
And then you have 20 minutes talk plus 5 minutes questions, and I'll give you 5 minutes when you still have 5 minutes for your talk.
Sorry, I'm confused. Give me 1 second. So it doesn't work if I'm in reader view. I have to be in reading view.
We could see your screen. It wasn't on presenter view. It was just we could see all the other slides as well, which is
okay.
That's the way you want to do it. That's absolutely fine. I think it's just not going to be presenting.
Okay. Give me 1 second. Can you see that?
That's perfect.
Ah, good. Thanks. So
Okay.
I'll talk about. Oh, you want to introduce
Go
me?
ahead. I already introduced you, but I can.
Okay, there we go. I'm going to talk
Go
about
ahead.
black holes, gravitational waves, and avenues to new physics. I'm going to start by talking about dark matter. Since this is a section on inflation and primordial black holes, I'll talk partly about primordial black holes and partly about inflation. One of the biggest problems we have in cosmology is the dark matter problem. As you know, what's it, 5.5 years ago, we saw the signatures of the first merging primordial black holes. The masses of these black holes were there were approximately 30 solar masses each. And now we understand that's as to be expected, but at the time it was kind of surprising because we kind of had in our mind that, you know, the most abundant stellar remnant black holes should have masses maybe in the 5 to 10 solar mass range. So this got people thinking. We were wondering, where do these black holes come from? They're probably stellar remnants. They might be in stellar binaries. They might be in globular clusters. But as I said, these first two black holes had masses which were 30 times the mass of the sun, which is big, although not necessarily unallowably big. And so some colleagues and I wrote a paper that was very speculative. It was not completely crazy. And we simply noted that there was an interesting coincidence. So if black holes of 30 solar masses make up the dark matter, they merge with a rate comparable to that inferred from the initial LIGO event. From that one LIGO event, you could figure out that there were, so many black hole mergers per gigaparsec cube per year. And it turns out that, we have some good idea about how dark matter is distributed in the galactic halo. And we know the total amount of mass in the galactic halos. And so if all the matter is made out of 30 solar mass black holes, you can calculate the rate at which they're going to pass by each other. And if they pass by each other closely enough and slowly enough, then there is a gravitational analog of a radiative recombination reaction that allows those two black holes to become gravitationally bound. So if two black holes are moving past each other with a fairly slow velocity, they will Rutherford scatter, and so their quadrupole moment will change. And if you have a time-varying quadrupole moment, there'll be gravitational waves emitted. And if the energy emitted in gravitational waves is greater than the kinetic energy of the system, then the system becomes gravitationally bound. So this is a straightforward calculation. This is a picture of a state-of-the-art simulation of the dark matter distribution in a typical galactic halo. And so we can take results of simulations like this to integrate over the entire volume of the galactic halo to figure out how often these things should merge. And the result we got turned out to be about 5 mergers per gigaparsec cube per year. And the reason that this is interesting is that it was in surprisingly good agreement with the merger rate inferred from that initial LIGO event, and in fact from the current LIGO events that we have now. There was, of course, a fudge factor because there are uncertainties that enter into this calculation. But a priori, you would have expected this merger rate to be 12 orders of magnitude too big or 12 orders of magnitude too small. The fact that you get the right ballpark is kind of an interesting coincidence. The other thing that we noted in that paper is that as of 2016, at that time, there was no empirical argument that could be used to rule out 30 solar mass black holes as the dark matter. 10 solar masses and below were ruled out by null results from Acho experiments in the 1990s and since then. But there weren't any constraints to 30 solar mass black holes. Since then, though, the scenario has been ruled out over and over by a number of different people. I don't want to say ruled out, I say many challenges, because there were a whole bunch of arguments that were made against primordial black hole dark matter, although none of them was actually, I think, fully robust. Each one of them had a number of caveats and knobs that could be turned so as to elude the constraints. However, I think that the scenario now really does face serious problems, and at least some people disagree with me, but I would say that the scenario has faced enough challenges that I'm no longer optimistic that it can be made to work. And the biggest challenge is primordial binaries. And this was work I did with Yassin Ali-Hamoud, Eli Kovitz, and Eli Kovitz. And the basic argument is simple and was actually presented even in the late 90s. If primordial black holes make up the dark matter, and if they're randomly distributed or smoothly distributed in the early universe, there will be, by chance, some regions where you have 2 primordial black holes that are sufficiently close that they will form a binary, a gravitationally bound binary. And then, if these things if these binaries are there, some of them will presumably survive until today and be merging until today. The question, though, was whether these binaries that are produced, in the early universe can survive 13.8 billion years of galactic mergers, etc. These binaries are subjected to subsequent generations of gravitational infall when they first form 10 to the 6 solar mass halos and 10 to the 8 solar mass halos. There are a lot of tidal forces, their interactions with baryons. And we evaluated this question carefully. We find that many of these binaries are destructive, but there was still enough to survive to exceed LIGO rates. So the issue is that there are enough of these binaries that survive that you would expect the rate for mergers of such primordial black holes to be roughly 2 orders of magnitude greater than the merger rates in LIGO. The result is not completely conclusive because there still may be other disruption mechanisms that are non-gravitational or that involve non-gravitational physics like baryonic interactions, which we do not take into account. So it's not necessarily completely ruled out, but these are the upper limits on the fraction of the dark matter that can be made of primordial black holes as a function of the primordial black hole mass. And these are upper limits from the null search, or actually from the current LIGO, not the current, the O1 LIGO merger rates. Still, if there is some reason that the scenario can be saved by primordial clustering, for example, we can use observations and experiment to test the scenario. So given the current LIGO rates that we've seen, it's not unreasonable to expect there might be on order of tens of thousands more black hole mergers detected in the next decade. And one of the characteristics of binaries formed from primordial black holes is that the black hole binaries are formed with an exceedingly or extremely large eccentricity. And with time, the eccentricity decays and the orbits circularize. But even at merger, there might be some small remnant of that eccentricity that can be detected. And so we looked at this in a paper with Elias Cholis, Yassin Ali Hamoud, Simeon Bird, Julian Munoz, Eli Kovitz, and Alvise Raffanelli. And what we forecast is that LIGO is probably not going to see enough events and have enough sensitivity to these eccentricities to observe or conclusively any or either confirm or disprove the scenario. But a next generation experiment like the Einstein telescope should see approximately 10 residual ellipticities. There's also the mass distribution for the black hole binaries. Ordinary stellar merger processes are expected to produce a fairly smooth number of events per merger mass. And if you have 30 solar mass primordial black hole binaries, you'll expect to see some bump on top of that. And again, this should be confirmable or disprovable within the next decade of LIGO type data. Another thing that's particularly interesting these days, now that CHIME has just announced the results, is lensing of fast radio bursts by primordial black hole dark matter. So there are things called fast radio bursts, which are millisecond flashes of radio frequency radiation, roughly gigahertz radio frequency radiation, that come, we now know with have good evidence that they now come from extragalactic sources. There are about 10,000 of those on the sky per day. And they have large dispersion measures, which imply that there are cosmological distances. And CHIME should detect thousands of these in the next few years, and they've already detected several hundred. Now, if the dark matter is composed out of primordial black holes, some of these fast radio bursts will be gravitationally lensed, and there will therefore be 2 images of that fast radio burst seen. Now, the angular separation between them is only approximately a nano arcsecond, and so too small to actually be resolved. However, the path lengths along these 2 different trajectories is slightly different. And so what you expect to see is the initial burst along the first trajectory. And then a little bit later, you'll see a second fainter echo from the second gravitationally lensed image. And so with time, you can look for repeating bursts. And we did a forecast, and what we think is that if the dark matter is composed of compact objects that have masses about 10 solar masses or larger, you should be able to detect that dark matter, even if it constitutes only roughly 1% of all of the dark matter in the universe. And I should say, I'll show you the next slide and then tell you something else. We wrote then another paper with Lingyuan Ji and Eli Kovitz where we consider looking for these echoes of gamma ray burst light curves. So the basic idea is gamma ray burst light curves are complicated, but you can actually develop echo detection algorithms. So it's possible to look at a given light curve and then see whether that light curve is actually a superposition of some gamma ray burst light curve plus an echo. And what we found is that gamma ray bursts are probably not too promising, but in current work with Beja, Lingyuan Ji, and an undergraduate student, Valeria Subirach, we are now trying to extend the fast radio bursts search down to a fraction of a solar mass. We believe we can extend this down perhaps by 3 orders of magnitude by looking for substructure within the fast radio burst. So that's it about primordial black holes, and I'm going to spend the remaining few minutes talking about some novel signatures of primordial gravitational waves that you can seek with the cosmic microwave background and with galaxy surveys. So with the cosmic microwave background, we measure not only the intensity, but also the polarization pattern. And the polarization pattern of the cosmic microwave background can be decomposed into E modes and B modes. And this is sort of an example or a cartoon sketch of what an E mode looks like. And this is what a cartoon sketch of a B mode. And as the picture indicates, if you look at this in a mirror, it is unchanged. But if you look at a mirror image of a B mode, it becomes, it has the opposite sign. And so B modes are odd under a parity inversion, whereas E modes are even. And so if there is some parity breaking physics that contributes to these polarization patterns, that should show up in a cross correlation between the E mode and the B mode. And if all the physics that gives rise to these polarization patterns is parity conserving, then there should be no E-B cross correlation. So these will show up in parity breaking temperature polarization cross correlations, the TB cross correlation, and also in the polarization cross correlation, the E and the B. The temperature has the same parity as the E, but opposite parity to the B mode. Now, it turns out that you can actually produce such a parity violating cross correlation if there is an inflaton field phi that is coupled to the Chern-Simons term of gravity. So here R is the Ricci tensor, the Riemann tensor, and R twiddle is the dual Riemann tensor. And there is a way to construct them, to construct a combination of R and R dual that is parity breaking. And such a term arises coupled to a dilaton field frequently in string theories. And this actually leads to a left-right asymmetry in the, or a breaking of chirality in the gravitational wave background, an overabundance of right circularly polarized gravitational waves over left circularly polarized gravitational waves, or vice versa, and thus to an EB and a TB cross correlation. There is also a 3-point correlation. There's also a 3-point correlation that can be constructed in the cosmic microwave background that is parity breaking. So here is a 3-point correlation function in Fourier space that couples 3 different Fourier modes on the 2-dimensional plane of the sky of wave numbers L1 and L2 and L3. And this triangle here is a parity inversion of this triangle over here. And we show that chiral gravitational waves can give rise to a preponderance of this type of 3-point function over this type of 3-point function. And then there are analogous things that you can do with three-dimensional surveys, with galaxy surveys. And this is work done with Liang Dai and Donghui Jiang. So we have an abundance of projects that try to map the distribution of three-dimensional distribution of galaxies in the universe. They are typically described in terms of a two-point autocorrelation function, the density at position x times the density at position x plus r. And this is called the correlation function, C of r. Now, typically, this is assumed to be statistically isotropic and homogeneous, which is a consequence or similar to translational and rotational invariance. So this two-point correlation function depends only on the magnitude r of the 2 points being correlated and not on the relative orientations. So isocorrelation contours are spherical surfaces if we assume statistical isotropy and homogeneity. So this is what isocorrelation contours look like in a statistically isotropic universe and a statistically homogeneous universe. The two-point correlation function is spherically has spherical isocontours, and those isocontours are the same everywhere in space, over here and over here and over here. But it's possible to have a departure from statistical isotropy, in which case isocorrelation contours or isocorrelation contours could be elongated in some specific direction. And there could also be a departure from statistical homogeneity, in which those elongations differ from one point in the universe to another. So these elongations of isocorrelation contours are analogous to the cosmic microwave background polarization, which is an elongation of an electric field oscillation. And the difference, though, is that this ellipticity, which is the elongation of the galaxy surveys, is in 3 spatial dimensions as opposed to 2 spatial dimensions. So elongations in 2 spatial dimensions are described by 2 degrees of freedom, which we call the E and B modes. Ellipticities in 3 spatial dimensions are described by 5 degrees of freedom, which can be mapped onto the 6 the 6 most general polarizations of gravitational waves. So in general relativity, there's only the 2 transverse traceless components, but there are also 2 vector-like components in which the elongation is oriented along a direction that, along a plane that includes the direction of the Fourier mode, which here is in the z direction, and the transverse direction. And then there's also 2 scalar modes. There's a breathing mode where the isocorrelation contours remain circular but vary in space. And then there's one where they actually they become elongated, but the elongation varies in this direction over here. Now, it is possible to measure these from a galaxy survey, and we wrote down the equations that allow you to do that. And it's also possible to construct a parity test. So we have 2 transverse traceless modes, H plus and H cross, and we have 2 vector modes, which we call HX and HY. And if you take a linear combination out of phase of H plus and H cross, you get a circularly polarized gravitational wave. Plus or minus tells you whether it's right or left circularly polarized. And there's something analogous that you can do with a vector-like elongation. And so you can actually look not only for gravitational wave type distortions to the 2-point correlation function, but also vector gravitational wave like distortions to the 2-point correlation function. And you could also look for parity breaking such effects. The last thing I'm going to tell you is an advertisement for some papers I wrote with Keisuke Inomata just a few years ago. So these theories predict, some of these theories of inflation predict that the gravitational wave background might be chiral. And it turns out that if you have a chiral gravitational wave background, that chirality can actually be imprinted on the chirality of the cosmic microwave background photons through a photon-photon interaction that then gets modulated by the gravitational waves. So in principle, if you could measure the circular polarization of the cosmic microwave background, and you were to find that it is non-zero, i.e. there's a preponderance of right or left circularly polarized photons, that could be a signature of chiral gravitational waves. This, however, is largely an academic exercise because it turns out that quantitatively, the circular polarization amplitudes that arise are extremely small. So I will conclude here. The first thing I told you is that 30 solar mass primordial black holes, I think, were a very interesting possibility for dark matter a few years ago. They are still a possibility. I would say that when we wrote our paper back in 2016, it was a scenario that was innocent until proven guilty. I think that it has now been proven to be guilty. It's now been found to be guilty and remains guilty until it's proven innocent. But there are a variety of ways that we can test this hypothesis with forthcoming gravitational wave and other astrophysical data. There are a variety of novel ways to use cosmic microwave background large-scale structure survey data to look for imprints of Hubble-scale gravitational waves that may have come from inflation, including chiral signatures of chirality in that gravitational wave background. And we need to keep thinking as theorists, as our experimental colleagues keep searching. Thank you very much.
Thank you very much. Very interesting talk. And we already have a question by Salvatore. To go ahead.
Yep, I hope I can be heard. Hey, Mark, thank you for the talk. I have a question, and also apologize about the noise. Someone is drilling just next door. About the first part of the talk, so the primordial black hole, in particular, the potential way of getting at it, looking for a bump in our otherwise smooth mass distribution of the black holes. And so exactly this one. So the caveat or the concern I would have in this case is that in fact we are, and when I say we, I mean here the LIGO Virgo chiral collaboration, of which I am a member, we already saw such a bump, but we interpret that not as an excess of black hole from PBH formation, but rather as black holes piling up at the bottom of the pair instability mass gap, pretty much. So I guess my concern with something like this is that astrophysics is messy, and there may be other ways in which one can create an excess of black holes on an otherwise rather smooth distribution. So I guess then following up, I was wondering whether going for a smoking gun, which would be either the eccentricity, as you mentioned, or maybe just purely the redshift. Like if you see something merging at Z of 40, where there are no astrophysical black hole, would be, you know, a more uncontroversial way of getting at it. And you know, so yeah. I guess what do you think would be the most, you know, bulletproof? You know, if as a data analyst, what do you want me to publish to convince you uncontroversially that those are primordial black hole? They cannot be anything else.
Yeah, there was a paper that argued that DESIGO would have sensitivity to mergers at redshifts, you know, 40 or so, you know, that are much greater than the redshifts at which we think stars form. So yes, I think that would be a smoking gun. The eccentricities would not be a smoking gun necessarily, because there are ways to form binaries gravitationally within globular clusters. So I would say a null search would be a null result. A positive result would not necessarily be a smoking gun. But definitely I think the most convincing would be mergers at redshifts much greater than, for black hole mergers before stars form, yeah.
All right, that's what I hoped you would say. In that case, if you're around on Friday, I'll be talking about next generation ground-based detector, and I will have some good news.
Yeah.
All right, thank you again for the talk.
That's a good advertisement for being there on Friday. Thank you. I think Anish, you had a question?
Yeah, I just wanted to understand. So, so you said about converting the chiral gravitational waves under some background external field to chiral photons, right?
Yeah.
So, so my question is that, so what is the background field? Is it some kind of external magnetic field or something that converts
So
into?
strictly speaking, what happens, and it's kind of complicated but straightforward, is that in quantum electrodynamics, there's an Euler-Heisenberg Lagrangian that gives rise to a photon-photon interaction.
Mm-hmm.
So as a photon propagates from the CMB surface of last scatter to the observer, it is passing through a gas composed of all the other cosmic microwave background photons. And those cosmic microwave background photons at any given point have a quadrupole. And so that quadrupole actually gives rise to a rotation, induces a circular polarization of a linearly polarized photon. So that's the physical mechanism that induces the circular polarization. And then if I have a gravitational waves, that will contribute to the spatial fluctuation of that quadrupole moment in a way that induces a net circular polarization averaged over the entire scatter.
I see. So, so my question is because is it very particular to the CMB photons? Because CMB photons is at a particular frequency, and we also have very high energy gamma rays, and that we can detect at a very high frequency as well. So, if this case that you're saying is not very particular to CMB, then maybe possibly you can also do it for photons with other gamma rays or other kind of photon detectors that we have. That is what I was thinking.
That's an interesting question. I haven't thought about it. That's an interesting question. I think the circular polarization, that the Euler-Heisenberg term will be much bigger for higher energy photons.
And
there are fewer high energy photons. I don't know what the technologies are to detect circular polarization of gamma rays. And then there's the other possibilities of 21 centimeter fluctuations. And that is a paper that we started to write but didn't finish yet. The prospects to detect circular polarization in the 21 centimeter radiation is actually better than with the cosmic microwave background. It's not, it's futuristic, but it's not completely unimaginable. But gamma rays, I don't know. I haven't thought about that. It's a good question.
Okay, I think that's a very positive note to end up. Let's thank Mark again. And these are Carmen Salvatore, which I refer you to. And in the meantime, if Gianluca, you'd like to share your screen.
Can you see it?
Yes, yes, you can. You may want to do full screen.
Yeah.
Okay, and it's a pleasure to introduce Gianluca Calgani, who will be talking about gravitational waves and quantum gravity. You'll have 20 minutes plus 5 minutes questions, and I'll give you a 5 minutes heads up.
Okay, first of all, thank you, organizers, for giving me this opportunity to present my talk, which will be a summary of recent results on quantum gravity and gravitational waves. So the basic question I want to ask is, can we probe the physics of quantum gravity with gravitational waves? The question is not simple to answer because gravitational waves, at least those that we have observed so far, have a very low frequency. So we wouldn't expect them to play to get any signature from quantum gravity. However, there are several attack points from where we can explore this issue. One is the production of gravitational waves. For instance, looking at modified black hole solutions or modified primordial inflationary spectra can lead to new physics. On the other hand, the propagation of gravitational waves is an entirely different chapter, and in some ways maybe even simpler than the first, which entails well, several tools like modified dispersion relations, the phase of a waveform, the luminosity distance, and again, primordial spectra. Here in this talk, I will discuss about modified dispersion relations very quickly, the luminosity distance very quickly, and then spend more time about the stochastic gravitational wave background. So modified dispersion relations, this is quite an old topic, and it has recently been revived from the discovery of LIGO, of gravitational wave sources. And this is a typical modification dispersion relation of a monomial type, where n in some stringy or non-commutative models is equal to 1 or 2, in which case the bound on the characteristic energy scale is extremely low. And however, one can ask oneself, for instance, okay, first of all, this bound comes from a bound on the propagation speed of a gravitational wave coming from GW 150914, and for well, for the observed frequency, basically this gives a very tight bound on the difference between the propagation speed and the speed of light, about 20 orders of magnitude, and this in turn can lead to a bound on this mass m, which is extremely low for integer n. However, one can reverse the logic and ask what n we would need in order to get a realistic energy scale above the LHC scale 10 TeV, and the answer is that n should be non-integer between 0 and 0.75. So this range is a typical of field theories that live on geometries of a multifractal type. Now, this is irrelevant for quantum gravity because it has been shown that effective geometries arising from theories of quantum gravity in general do have multifractal properties. So in turn, this parameter n is related to the Hausdorff dimension of space-time in the ultraviolet. So in particular, for a typical value of this Hausdorff dimension 2 near the UV, the typical energy scale of these models should be around the Planck scale. Anyway, this is just these are quite simple simple ideas on how to use modified dispersion relations. However, there are other ways in which we can probe physics beyond Einstein gravity, one of which is the luminosity distance of gravitational waves. The latter, well, can have various definitions. I like this one, which is fairly simple, which is the luminosity distance of gravitational waves is the inverse of the gravitational wave amplitude. So in general relativity, this amplitude is actually proportional to the inverse of the luminosity distance of the electromagnetic counterpart of a source. So in general relativity, these two luminosity distances are the same, and the ratio is equal to 1. Actually, we have only one example of a standard Sirian that is a source of both gravitational waves and photon, and which was observed by LIGO. But we expect to find about 70-80 standard Sirians with LISA. So we would have actually, we worked with simulated catalogs, simulated sources of what we could observe from LISA to test a new relation between these luminosity distances, which can be encoded into this expression, where gamma is a parameter which I will discuss briefly shortly, and L star is a characteristic scale of a model. So the claim is that in quantum gravity in general, this ratio of luminosity distances, which are measured separately, independently, this ratio is of this form in general in quantum gravity. And actually, in a couple of papers which we published a couple of years ago, we found that quantum gravity effects could be detectable if this parameter gamma is slightly larger than 1, even in the case where this characteristic scale is not cosmological, but is actually a Planck scale. So where does this parameter gamma come from? Well, this is just a sketch. I don't really want to go into much detail, but basically in quantum gravity, we would expect that two main changes in the dynamics of the gravitons. One is at the level of the space-time measure, and the other one is at the level of the kinetic term acting on the graviton. In terms of these two types of corrections are related to the geometry of space-time itself. Now, the dimensionality of this of the graviton will depend on the scaling of the measure and the kinetic term, and we can call it capital gamma. And it's not difficult to show that the general solution of a linearized equations of motion for the graviton should scale as 1 over r to the gamma, where r is a distance in what is called the local wave zone. But at cosmological scales, this r becomes actually the luminosity distance for an electromagnetics for a source of photons, and so you have this anomalous scaling. So in GR, this capital gamma is equal to 1. Now, in general, this capital gamma can be larger than 1 in some models, and this happens. These are simulated profiles of gamma as a function of a scale, and this happens for very, very few models of quantum gravity. In fact, only for 3 classes. One is a no-commutative models living on Kappa-Minkowski. The other is a model by Padmanabhan on no-local black holes. But these 2 classes of models predict a gamma above 1 by around by more than 100, by less than 10 to the minus 120. So this means that this gamma is really so close to 1 that any effect will be totally negligible. The last class of models of quantum gravity actually come from loop quantum gravity, spin forms, or group field theory, which all share the same kinematical states. And in that case, it is possible actually to get the geometries, effective geometries, where you have this bump above the asymptote 1, and so gamma is slightly above 1. So now this capital gamma is actually coincides with this phenomenological parameter small gamma. And so eventually one finds that although it is very, very difficult, it still may be possible that some models of quantum gravity would detect a deviation of a luminosity distance with respect to the paradigm of general relativity of a magnitude sufficient to guarantee detection in LISA. Now, the luminosity distance actually strongly depends on the evolution of a universe, and in particular on the dark energy component. So with cosmology working group in LISA, we explored models beyond the general relativity, not necessarily quantum gravity, but also phenomenological, to see how they would affect the luminosity distance of gravitational waves. Here, as a new avenue, let me just advertise something which I've recently published in Classical and Quantum Gravity, which is a no-local theory, which I tried to construct with the aim of getting unitarity and renormalizability at the quantum level. I wanted to make basically a perturbative quantum field theory of gravity. This turned out not to be possible for this type of no-locality, for technical reasons, which we may discuss in discussion sessions if you want, otherwise we can just skip them. But basically, although this model is not successful as a theory of quantum gravity, it does predict infrared corrections where the theory is actually stable. So the background is stable, and the theory does, and also the theory does not have divergences in that region. And this correction to GR is no local because it's a fractional power of a D'Alembert, and for certain values of this parameter gamma, which has nothing to do with a small gamma we discussed about the luminosity distance. Sorry for using the same symbol. For certain values of this parameter gamma, this reproduces models of infrared no-local gravity, which were considered by Barvinsky, by Maggiore's group, and that are known to give rise, that are this type, so where you have inverse integer powers of D'Alembert, which actually are known to give rise to strong deviations of the luminosity distance of gravitational waves. So the hope is that with this new model, we could get a similar phenomenology, with the advantage that this model has a motivation in terms of having been built on a geometry with multifractal properties. And this is where the connection with other models of quantum gravity will come from. Now, let me now go to the topic of the stochastic gravitational wave background in the last 7 minutes. In general, well, we have seen in today's session the basics already. So let me not delve too much into it. Although we have successful models of inflation like Starobinsky inflation, these models in general predict a very low tensor to scalar ratio and a low amplitude for the stochastic gravitational wave background, which is a derived product from primordial gravitational waves. And in particular, for Starobinsky inflation, the stochastic background is slightly rather tilted. It means that it never increases. So in general, to get a detectable signal in present and future experiments, and here you can see this is the LIGO-Virgo-Kaga curve, and these are the projected curves for LISA, for the Einstein telescope, and for the SIGO. In order to get a signal detectable by these experiments, we will need a blue tilted spectrum. So the question is, since we cannot realize it in standard slow inflation, can we do it in some models of quantum gravity? This is just a brief reminder of Starobinsky inflation. So since we've seen it already, let me skip. I just mentioned here that the tensor to scalar ratio is quite small, around 10 to a -3. And this is a simplified relation between the primordial tensor spectrum and the stochastic gravitational wave background, where t squared is the transfer function. This transfer function scales differently with the comoving wave number, depending on whether the universe is matter dominated or radiation dominated. It's important to notice that in the case of a reheating phase, this scaling would produce a damping, which actually turns out to be crucial for what follows. So, how many models of quantum gravity generate a blue tilted spectrum? We looked into many, and eventually we could select 5, which are these, and I will discuss them shortly. And more details can be found in a paper recently published with Sachiko Kuroyanagi. Okay, one model we consider is no-local quantum gravity, which has a form similar to the one I showed you for that dark energy model, except for the fact that the operators, the no-local operators, are not fractional powers of a D'Alembert, but are entire functions of this operator, and such that they tend to one in the infrared. This is a perturbative quantum theory quantum gravity, which where unitarity is preserved and renormalizability is improved, and it's free from Ghost degrees of freedom on a Minkowski background. An advantage of this theory is that it can embed no-local it can embed the local Starominsky inflation naturally, because one can construct form factors such that in a specific limit, one obtains a no-local version of Starominsky inflation with basically the same type of good properties, which, however, predicts a blue-tilted spectrum at the CMB scale. So here the hope was that we could get a detectable signal. However, this is not possible. Let me just state the general reason. And the general reason is that although the spectrum, the tensor spectrum tends to be blue tilted at the CMB scales, eventually it does not arise enough to reach the sensitivity curves of this cycle. So eventually it tends to the standard Starominsky inflationary spectrum at a very high frequency. Okay, so this model actually taught us that a blue tilt at the CMB scale does not always mean a detectable signal at interferometer scales. The other models we considered didn't have.
Okay, you have 2 minutes.
Yeah, we didn't have this problem. We consider a model where inflation was realized on non-commutative space-time, and here the model did reach barely the de-Sigo scale, the de-Sigo sensitivity curve. Other models based on multifractal geometry basically reach the same conclusion. And in the case of other models proposed by Robert Brandenberg, like string-gas cosmology, here the signal is higher, but it doesn't reach a Einstein telescope. And finally, this is the new ekpyrotic scenario, which is a recent version of the ekpyrotic scenario, which respects all CMB constraints, and furthermore, it can reach the sensitivity curve of the Einstein telescope. Let me mention also that in the case of if the accelerated expansion at the beginning is followed by reheating phase, then the spectrum is damped, so it never reaches the Big Bang synthesis bound. So this blue curve is basically safe, is not excluded already by BBM. To conclude, gravitational waves can become a powerful probe of quantum gravity, both in the very early and in the later time universe. Dispersion relations in general are tightly constrained, so that avenue for the moment seems not very promising. Luminosity distance of standard science, however, can yield important information on gravitational wave propagation in quantum gravity, and we are still looking into this matter also with a cosmological working group in LISA. And finally, some models of quantum gravity or motivated by quantum gravity can predict a stochastic gravitational wave background detectable by the SIGO or the Einstein telescope, although unfortunately not by LISA and of course by LIGO, Virgo, and Cabra. Thank you very much for your attention.
Okay, thank you very much for this very interesting talk and for being so much on time. We already have a question from Anish on the chat. I don't know if you want to reformulate it, Anish, say it aloud. Okay, Anish was asking if you have a detectable signal if non-locality is present in the matter sector, non-local scalar field, say, but with local gravity sector.
In general, well, if you mean no locality of UV type, so in something one would hope to be a theory of quantum gravity, then it depends on how you couple matter with gravity. So in general, we expect to have a no locality in all sectors, including matter.
Okay.
I don't know if this answered, but in general, here we concentrated on tensor perturbations. If you're thinking about the scalar perturbations, then it really depends on how you couple the scalar field with gravity. There are constraints on no local inflation with no local scalar field.
Okay, thank you. I don't know if that answers Anish's question, but makes sense to me. Salvador, you have a question?
Yes, thanks, Gianluca. Sorry if you said this and I missed. There is some element of distraction in my apartment right now. What kind of uncertainty would you need on the measurement of the luminosity distance from the gravitational wave sector to be able to set interesting constraints? Are we talking of sub% level?
Look, this constraint is based basically on the LISA uncertainty, which is for a redshift smaller than 1 is between 10 to the minus 3 and 10 to the minus 2. So it's below the percent level. When when the redshift is greater than 2, is the uncertainty of luminosity distance reaches the 10%, which is quite big. But here the question is also, given that uncertainty, what would we need from this parameter gamma to have a detection? And this answer should be slightly bigger than 1. So I prefer to answer your question in reverse. So given the uncertainty of an experiment, what can we do with the parameters of a model? So, but this is worked out for actually, yeah, I would say for a order percent uncertainty. So it's quite large. I mean, it's the one we have with present and future experiments. The DCIGO will do better by 1 order of magnitude, but the Einstein telescope will have the same error bars as LISA, as far as I understand. So this is the answer for the uncertainties we have.
Maybe a bit larger than LISA. The one thing that I have on mind, by the way, Claudia, feel free to tell me to stop whenever you want if we're late, is that at least on the ground, of course, we have a source of uncertainty, which is not often mentioned, which is instrumental calibration, which are needed to convert a voltage into a strain, right? And I never managed to get an answer from the LISA folks about what kind of calibration errors they expect to get. But that it's something that it's not always mentioned in the literature, but it's always there. And for us right now in LIGO, that is of the order of 6 or 7% uncertainty coming only from the calibration. And even if the signal to noise ratio increases, you still will be, limited eventually by that number. It will get a bit better as the instrument improves, but not that much better. Okay. So I would expect something similar to happen in space. So if you need a statistic of 10 to the minus 3% in the luminosity distance, but then you have a 1% on calibration, you add them in quadrature, 1% is going to win.
I'm afraid that your question is too technical for me, and I don't really have an answer.
No, it's not really. It's a warning more than a question.
Okay, yeah.
Well, at this point, it's something worth checking out.
I will ask, because I think it's an interesting thing. I don't know if people considered this a source of I guess they did, but I prefer not to say anything specific because I'm not sure about it.
Okay, thank you very much. Is there any other quick question? If not, let's thank. Sorry, Yanu, you had a question.
Yes, so I want some more clarification on the BBM bound that you were talking about. Can you go back to that slide? Yeah, like this one. Yeah, so you see the BBN, you mean like a delta N effective for the total radiation energy density, right?
Yeah, so this straight curve would hit the BBM bound if we were no reheating phase after, well, in this case, we cannot talk about inflation, but about the ekpyrosis. However, since the reheating is expected, metal production is expected, in general, this bends back down the signal. And the reason is that the transfer function scales as a K2 minus 2 in a matter phase. So reheating is an early matter phase, and it's where this suppression kicks in.
Let's see. So you do have a cutoff. I was just thinking if it keep rising, then it's still a problem.
Sorry, I didn't understand what.
Well, I said so. You do have a cutoff by the reheating for the spectrum. So
yes,
that's otherwise it would keep rising.
Yes,
so.
But it's a very it's to the far right. It's well beyond this this figure. But in general, yeah, it's because of this that you get this suppression.
Okay, thank you.
Okay, thank you very much. So I think now it's a good time to thank Juan-Luca and all the speakers of this afternoon. And I don't know if the organizers want to take over.
Yes, thank you, Claudia. And yes, thanks again to all the speakers. So I believe this concludes our second session for the day. So now the plan is to have a 5-minute break. So we'll meet at 6:20 for the discussion session. And again, to all the speakers, if at all possible, we'd be very grateful if you show up for the discussion. Thank you. See you in 5 minutes.